we will have Professor Sonia Seneviratne from the Land Climate Dynamics at the Institute of Atmospheric and Climate Sciences, ETH in Zurich. And she has been involved also a lot in IPCC process. And in the last, there was a special report on extreme events. She was one of the coordinating lead authors. Mm-hmm. She also was one of the lead authors for the IPCC special report on 1.5 degree report, which was released last year. And also she is working currently as a coordinating lead author for the ongoing AR6 assessment working group 1. She's really internationally well-known expert on extreme events because she's taking care of the ongoing IPCC chapter on the extreme events. So the floor is yours, Sonia.
Yeah, thank you. So it's working? Yeah, okay, great. Yeah, thanks a lot to Deliang and the organizers of this event. It's a great pleasure to be here. So in my presentation, I will give an overview mostly on assessments of changes in climate extreme based on the 1.5 report and also more recent evidence. So I will talk about climate extremes in a warming climate at 1.5 degree, 2 degree, and also higher levels. I've included some pictures here of the IPCC 1.5 report authors. So of course there were a lot of people contributing to this report, and also we'll show some results from our research group at ETH in Zurich, and so I've included a picture here as well. So so this will be a rather general overview. I will show also a few more detailed results. So just to remind you, about a bit more than 1 year ago, the special report on 1.5 degree warming was approved by IPCC. So it's already 1 year. And I think it was quite an important event. It did, I mean, the assessment that was done there obviously had a high policy relevance because IPCC special report 1.5 degree warming had been actually requested as part of the Paris Agreement. So if you remember, within the Paris Agreement, almost all of world nations have decided to limit global warming well below 2 degrees and if possible at 1.5. So the main question that was asked from IPCC was, what is the difference between impacts at 1.5 compared to 2 degrees? Is it worth it to really make this extra effort to limit global warming to 1.5? And the other question was, to which extent could we still reach 1.5 or limit global warming to 1.5 degrees? Maybe also to provide an additional context, also here in Sweden, I think some of the results of the report have received a lot of general attention, in part thanks to Greta Thunberg and the movement she has started, Friday for Futures. I won't say too much about it, but I think the main message of this useful movement in the end is listen to the science, which I think as scientists probably we should welcome. And that was certainly a reason also why the report got a lot of attention. So I will just present first a few general conclusions from the report. And the first point is, where are we at the moment? And the point is, in the past, we used to speak of climate change as something that would happen very far in the future. And now we have to recognize climate change is happening now. We have already 1 degree of global warming. So this is showing that basically climate change is happening already now, and we have impacts associated with that. So this is the 1 degree of global warming is the average human-induced global warming we had in 2017. Now, another evidence, and that's already since IPCC ER5, there is a clear link between CO2 emissions and global warming. So that's now really very, very well established. And actually, this link is very straightforward because CO2 stays very long in the atmosphere, on average, up to several hundreds or even to several thousand years. It means that basically what matters is the total cumulative CO2 emissions since pre-industrial time. So the overall stabilization of global warming depends on the cumulative CO2 emission, and the relationship between the two is almost linear. Which means that if we decide, we know at the moment we have 1 degree of global warming, if we say, well, actually, we shouldn't go above 1.5 degree of global warming, this gives a very clear target in terms of total CO2 emissions we shouldn't exceed, and gives a clear goal. So, as mentioned, we had 1 degree. We see this is basically the result of the emissions we have had so far. which means that we have a very limited budget of CO2 we can still emit before we reach 1.5. After that, we would basically need to have a net zero CO2 budget. So if we don't do anything, we are going to reach 1.5 degree of global warming in about 2030, plus minus. And I think that's another important message. So one reason maybe why action in terms of mitigation was not so strong is that sometimes there is the idea of maybe we should wait and see if we have a better solution in the future. The problem is if we don't do anything, because CO2 keeps on accumulating in the atmosphere, the situation gets worse and worse. So lack of decision or lack of action does not imply no change. It's also a choice by itself, and it's actually a bad choice because we keep on moving on this line here more and more. Now, just to say, what is this climate we are facing now with 1 degree of global warming? I think in recent years we have seen already now very extreme events which illustrate that basically it's already having strong implications. So for instance, 2018, there was a range of extreme events across the Northern Hemisphere, in Europe, also North America and Asia. I think in Sweden, we were strongly affected. There were fires in Sweden. But for instance, also in Japan, there was a heat wave and also a heavy precipitation event. Several people died in Japan of the heat wave. At the same time, there was also a heat wave in Canada. Many people died also of the heat wave in Canada. We think it's a cold country, but actually they died of the heat wave. Then there was very dry and hot weather in California, which led to forest fires in summers and again in the fall of 2018. And now, as you know, there are again fires. In France, there were very hot temperatures, also 2018, but for instance, in 2019, this summer, for the first time, 46 degrees was reached. And it was a little bit ironic because a lot of climate scientists were at a conference in Toulouse, which I was also at, was on statistical climatology. And so, for instance, I was traveling by train on that day, and it was extremely hot, so I can confirm that. So, yeah, it was very extreme. Then recently there was, of course, also tropical cyclones, and Kerry is going to say much more on that. I just want to mention, for instance, the tropical cyclone Durian. And so we know that the frequency of tropical cyclones is not necessarily affected by climate change, but the intensity of precipitation associated with tropical cyclone is affected by climate change, which obviously is linked to impacts. So there are already detectable changes in the climate system, and this can be attributed. This is evidence we have from the literature. And so maybe just to remember, this can be attributed to human CO2 emission. In the end, this means it's mostly due to the consumption of fossil fuels. And so those changes that we can already detect and attribute to anthropogenic climate change, so human-induced climate change, are increases in heat waves and hot extremes in most land regions, an increase in heavy precipitation at global scale, also increase in drought in the Mediterranean region, and more intense precipitation associated with some tropical cyclones. Just to illustrate one example, for instance, a change in hot extremes. This is analysis I've done with colleagues in Australia, where we're looking at the total land area affected by the exceedance of hot extremes. And we clearly see a very strong increase, for instance, since 2000. Obviously, we have a threshold that is then reached much more frequently, but we see that there are more and more area of the total land that is affected by hot extremes. So the 2015 Paris Agreement suggested to try and make all efforts to limit global warming to 1.5. Is it worth it? I mean, we already have 1 degree. Now, the other decision is to try and limit below 2 degrees, but does it make a difference if we have 1.5 versus 2 degrees? That was the main assessment in the report, at least for our chapter on impacts. And maybe one point that is really important to make, I mentioned this also to Kerry, Emmanuel today, because in some studies, in economic studies, apparently there is not always consideration of regional change in climate, but when we have a change in global warming of 1.5, obviously there are not all regions that are all warming by 1.5, and also not all the time. So does the 1.5 global warming target implies 1.5 degree warming everywhere and all the time? The answer is no. I think most of you will know it, but so obviously we have much more warming on land. So this means Of course, at 1.5 doesn't sound like a lot, but it implies actually much more warming when you look at land region, and particularly if you look at extreme events. So for instance, these are the change in hottest days when you reach 1.5 degree of global warming. This is a change in temperature of the coldest night. And so you see in many land regions, obviously we are above 1.5, but we are between 2 and 3 degrees of global warming. And in this case here, we are actually at about 4.5 degrees of global warming. Not sure if it's the right scale, but anyways, that's about doubling, and this is 3 times warming. So now we have a much stronger warming of land extremes compared to the global temperature. We have also illustrated this in a study published a few years ago. And so, interestingly, if you start looking at changes in hot extremes at regional scale, you find a strong relationship between the change in hot extremes, for instance here, and global warming, an almost linear relationship. And so this is a change in the temperature of the warmest day of the year in the Mediterranean in all of the climate model simulations, so SEMI5 simulations. In red, we have one scenario, RCP 8.5, that's the one that is warming the most. RCP 4.5, you have less emissions, so it's a different time scale, but the relationship is almost the same. And this would be the 1-1 line. So clearly, the hot extremes are warming more than the global mean. And so you see this increased warming here. And also this means from those simulations, for instance, you can derive changes at different levels of global warming. Now, this dependency is quite different if you look at different regions. For instance, in Central Europe, you see that that's a multimodal mean. So that's the lines are showing multimodal mean, and then the total range is showing the total range of available simulation, the average for 10 years. And for instance, in Central Europe, we find a very strong spread between models. And in this case, we have some models that have only about 1 degree of global warming of hot extremes when you have 1.5 degree of global warming, but some have up to 5 degrees of warming. Now, I won't have time to discuss the detail. Much of this is related to feedbacks with land atmosphere, for instance, how much drying you have in this region. Now I'll come to this question of whether it makes a difference if we have 1.5 degree versus 2 degree. Again, it doesn't sound like a lot. It's only half a degree of global warming. Here, this is an analysis that is looking for those big regions from IPCC, whether we can statistically detect a change in extremes when you are reaching 1.5 degree of global warming versus 2. And so the first line here is for hot extremes. The second is for the coldest night temperatures, RX 5 days, heavy precipitation. The last one is CDD, it's consecutive dry days. And so if you have colored shading, it means that there is a statistically significant differences. And you see for all of the regions very clearly, there are differences in extremes. So you have more extremes, so hot extremes, both actually during the hot season and also during the cold season or during the night. So very clear increase of those extreme temperatures in all regions, actually. For heavy precipitation, many regions show a significant increase in heavy precipitation, as you can see here. For drying, it's a bit less clear, so there is not really a global signal, but some regions are showing a clear tendency towards increasing drying. This is only one measure. You can use some other measures, but for instance, a lot of measures show increased drying in the Mediterranean regions. And actually, in this case, we have also a signal in Central Europe. So there are a few regions which show drying, and actually also Southern Africa is one region that is showing a signal here. So I come now to the main conclusions we had regarding difference in extremes between 1.5 and 2 degrees. So we found that the limitation of global warming to 1.5 compared to 2 degrees limits a large increase in substantial additional changes in extremes and impact. So it would limit the increase in hot extremes in most inhabited land regions, also increase in heavier precipitation in several regions, as I've just shown, and increased drying in some regions in Mediterranean and Southern Africa. So the signal gets stronger when you look at 1.5 versus 2 compared to what we had now compared to the past. Yeah. And I think this is a particularly important point. And in our chapters, we were looking at extreme, but also impact. So that's part of the assessment that was done by other scientists. We have also some irreversible impacts which are associated with those changes. So for instance, one irreversible impact is a further increase of sea level rise, and also extinction of some animal and plant species, in particular coral reefs. And so that would be also a main argument for saying that it is worth not going above 1.5, because we are starting to come in the range where things are happening that we basically cannot reverse. Yeah. So to look at this dimension of impacts, basically we had this assessment here, which was looking at a range of systems which are affected by change in climate, including extremes. And so this way of presenting this is called burning amber. And if, for instance, we look at warm water coral, so the idea is if you have white, it means you cannot detect any change, any risk. Yellow means moderate risk, red means high risk, and purple is very high risk, and that's when you start to have irreversible impacts. And you see that, for instance, for coral reefs, so now we have 1 degree of global warming, we are already in the range of high risk. So, for instance, even if we manage to limit global warming to 1.5, we would already get into this very high risk range. So we would already have extinction of coral reefs in many regions. But we would still limit the impacts compared to conditions you would have with 2 degrees. Other important effects are, for instance, the Arctic regions, where you have a substantial change also from 1.5 to 2 degrees. And actually, most of those systems obviously are always showing more impacts at higher levels of global warming. The exact thresholds are different depending on the system, but you can distinguish basically what are the impacts at 1.5 versus what are the impacts at 2 degrees. So we have, and that's really particularly important aspect, is that we have irreversible impacts above 1.5 degrees, but in general we also have more impacts overall at 2 degrees compared to 1.5. I also wanted to show some of those results. Actually, this is from the SR Land report. It shows that another conclusion, maybe illustrates also another conclusion of the 1.5, which was that every half a degree of warming matters. So maybe that's for other systems. We also hear quite a bit about, so for instance, wildfire damage. So this was not done at the time of 1.5, but we have new evidence on this showing that here at 1 degree, we are starting to have moderate risk of increased fire impacts, and 1.5 we would get into high risk, and so obviously this is also worth basically limiting global warming in terms of reducing fire risk. In terms of food supply instabilities, the assessment of the IPCC land report also suggests increase in risk for a level of global warming. And for instance, in this case, at around 1.5 degrees, we get to high risk, and we would get already almost at very high risk at 2 degrees. And I'll discuss this a bit later. This is in part also related to the issue of compound events that you could have, for instance, several breadbasket regions affected by extremes at the same time. Another point that often comes up is also the issue of tipping points. So obviously, that's an area in which we have quite a lot of uncertainty. We don't have very precise numbers, but there was an assessment that was done in the report of what is the risk associated with global tipping point. This is, for instance, from a study from Jeffrey et al. In PNAS, and they have looked at when the global tipping point might be reached in different climate simulations, and in many cases, they were reached between 1 degree and 2 degrees. That's when you have yellow shading. So there is an increased risk of reaching those tipping points. And there's also probability is low, but there is increasing risk, obviously. So the assessment from the IPCC 1.5 report was at the time, we have more or less moderate risk of reaching global tipping points. And we'd get to high risk around 1.5, and then obviously above 2 degrees, we'd get to very high risk to at least reach one of them. Some global tipping points are associated with extreme events, for instance, forest dieback in the Amazon region, so it would be a combination of droughts and possibly also deforestation. Now I want to say, present some other results where we show that obviously climate models are not perfect, but we shouldn't take this as a reason for not acting, because in some cases it might mean that the model is actually underestimating risk. So this is a study from our group by Vincent Humphrey, and it was looking at global data of water storage on land versus CO2 growth rate in the atmosphere. And we found a very clear relationship between the two. So that's basically on global scale. We find that the two data sets are fully independent. We find that whenever there is less water storage on land, so it means on average we have more drought conditions, we have a clear, strong increase in the CO2 concentration in the atmosphere. So it just suggests a direct relationship, which means that if you have drier conditions, you have less CO2 that is taken up by ecosystems, which is why you have then an increase in the CO2. This is a problem in the context of projections, because if we, for instance, had more droughts in regions where you have a lot of CO2 uptake, for instance, in tropical regions, obviously this could include a feedback that then increase further warming. What we found was in climate models, this relationship is underestimated. So we found the correlation is present in models, but it's only about half. So models are actually not representing this very well, and they are possibly underestimating this feedback. This is just an illustration to show that this is really important, because about 1/4 of all emitted CO2 is taken up by the land. So it means that if, for instance, you have more droughts and this affects this sink for CO2, obviously this would have global consequences. Finally, I also wanted to mention compound events. This is a new topic that we're also assessing in our chapter. There is emerging literature on this. So the idea is here to look at compound events, so multivariate extremes, because much of the literature is focusing often on single extremes, for instance, change in heat wave or change in droughts. But you can also have compound risk from the occurrence of two types of extremes. For instance, if you have at the same time hot and dry conditions, this will increase the fire risk. Also, if you have sea level rise and heavy precipitation, you can have more storm surges. And so this is a topic that is emerging, and the idea is, for instance, here you would have the area of risk, and you have those two climate drivers. If you were only to look at this driver, and this is where you expect increased risk, you might assume, if you are not considering the other drivers, that you actually don't really have an increase in risk if you have an increase in these drivers. The increase in risk only comes when you look at the combination of the two drivers. And so this is an emerging topic, but there is still not a lot of literature on this. And a particularly important issue is that some of those drivers might be correlated, which means that they happen more frequently together. And it means that those compound events would happen more frequently than what you would expect by chance. So statistically, you would happen to them to happen just randomly, but actually because they are correlated, they happen more frequently together. And some example of this is fire risk, because droughts and heat wave are correlated with one another. When you have drier conditions, you have then hotter air temperature because of more sensible heat flux, and higher temperature can lead to dry. Also coastal floods, which is related to sea level rise and heavier precipitation, both of which are affected by climate change. And for instance, heated pollution, so when you have at the same time high pressure system and stagnant air. I want also to illustrate another issue related to these compound events that's more in space. So when you have events happening at the same time at several locations, I mentioned already the 2018 conditions where we had this range of hot extremes and dry extremes across the northern hemisphere. That's a study from Marta Vogel in our group. So we looked at how much of the total area in the northern hemisphere we have people living or we have agriculture was affected by hot extremes. And we find that a very large fraction of it was about 22% of the total area. Now we looked at to which extent was this event unprecedented. We found that in observation, it's unprecedented, so the probability here of exceeding 20% here was very low. In observation, basically, it didn't include this event. That was the first time it happened. But also in climate models, that's a gray shading here. Actually, this event was not included. So if you look at the past, it was certainly unprecedented. But what we found was, if you look at the climate simulation for 1 degree of global warming, this event should not have been unexpected, because at 1 degree of global warming, this type of event is very likely. Well, it was not very likely, but it has a high probability, because we had about 1 out of 6 years would have this type of conditions, about 16%. Now, what we found was, at the time, it was felt like it was very extreme condition, But at 1.5 degree of global warming, we would have 2018-like events, so such a large fraction of inhabited and agricultural areas affected by hot extremes every 2 out of 3 years. And at 2 degrees, basically every summer would look like this. So this also putting things into perspective. Now, some of the issues is obviously you could have bread baskets, different locations affected at the same time, or if you could imagine that, as I think also here in terms of the fire, there were some issues that neighboring countries had to help, but now if you had several neighboring countries affected at the same time by fire, at some point you could also imagine that this affects the response to the extreme. So finally, I come to the mitigation point, because this was an important point in the report. What can we do if we want to avoid global warming of more than 1.5? So basically, the emissions so far, and that's I think also another main conclusion of the report, they do not commit us to a world with more than 1.5. It's really our decision. But the required change, if you want to limit global warming to 1.5, are really without precedent. So we need immediate reduction of CO2 emissions. Until 2030, we need to have only 50% of CO2 emissions we had in 2010. And we need to reach net zero CO2 emissions at the latest in 2040, 2050. So we need to move very quickly to a system where we're not emitting any CO2 anymore. Just to remind you where our CO2 emissions coming from, a very large fraction is coming from coal consumption, also oil, partly gas, and land use change is also not negligible. I want to finish with this, which is about trying to assess what are the impacts, so how much a change in climate is too much. I was asked to give a talk on this topic, and I find this is coming often because the question is, okay, do you stop at 1.5 or 2, and maybe if we have more warming? So how do you determine when it's too much? And I tried to use this analogy. I'm not showing, some people found it useful. So the analogy I was using was we are on a platform, and this platform is increasing, because every time we are emitting more CO2, it's getting higher. So there's no coming back. That we know about this. And now we are more or less at 1 degree. The analogy is we are at 1 meter. And you know, there is some wind, so people can fall down. And maybe if you fall down from 1 meter, okay, it's not so nice, but you twist your ankle, it's not too bad. Now, if you were to be at 1.5 meter, yeah, maybe if you fall badly, you could break your leg. It's not so nice, but you're still probably not dead. At 2 degrees, you could have multiple injuries. Maybe some of them will be irreversible. That's a possibility. And so it's a reason probably you want to avoid this. Some people might say, yeah, but probably most people are not going to die, so it's okay. I mean, it's a question of perspective. One important point is, again, there's this whole question of vulnerability, the fact that some people, for instance, a baby who would be falling from that height certainly would die. So you need to consider this. And then maybe if we come to 3 meters, you would have irreversible injuries. And possibly at 4 meters, we don't know exactly when, most people would die. Yeah. And there are some tipping points. So at some point, maybe this platform is becoming unstable. We know it's probably going to happen because it's not going to hold forever. We don't exactly know when, but we think maybe between 1.5 and 2, it's getting a bit more dangerous. Essentially after 2, the risk is getting even higher. And so this is showing that, well, every additional increase matters. I mean, you are just increasing risk more and more, and at some point we need to stop. Whatever we do, at some point we need to stop. We can stop not at 1.5 or at 4 degrees at any point. I mean, we don't want to go to, we need to stop this process. And the earlier the better. I think that's a message I want to give here. So some people could argue about adaptation. Yeah, maybe we can strap ourselves to this platform. Well, first, it depends on means and capacities. It's also the issue of climate justice. Not everybody has the same means to adapt. And so the science, the main fact is that science is showing we are increasingly putting ourselves and our environment at risk, and we need to stop at some point, and again, the earlier is better. Also, I wanted to take another analogy with where small increase in temperature matter a lot, for instance, for health. In this case, we don't say, when you have 40 degrees, it's only 3 degrees anomaly. You don't say it doesn't matter. And actually also already at 38, when you have 38 degrees, and you have a bit of fever, you start to be a bit worried. See, if you have this all the time, maybe you have some health issue. And in this case, maybe again, if it's a small baby, you are going to be even more worried. So in this case, we are also able to take into account the impact of small changes. So we understand the concept of different vulnerabilities, also in the case of health, and we care also about others' well-being. If others are sick, we are maybe trying to get them to the doctor and make sure this stops. So can this be extrapolated to climate change? Can we try to do something about this? And in the end, not taking action is negligence. So I come to the conclusions. Extreme events belong to the most visible and impactful consequences of human-induced climate change. Under present climate change, at the moment we already have 1 degree. We are seeing changes in extremes that are substantial. And there's a lot of extreme events are occurring now that would not have happened without human-induced climate change. There would be substantially higher risk from extreme events at 2 degrees compared to 1.5, and that's one message of the 1.5 report: every half a degree matters. We should say that several risks are not yet well assessed. For instance, the compound extreme events, so the effects of multivariate extremes for risk, and also the co-occurrence of extreme events at several locations. Finally, in terms of decision making, we are at a crossroads. We are not on track. I mean, to say, obviously, if we stop everything, we could limit global warming to 1.5. But if you look at what is happening in reality, the present commitments would lead us to more than 3 degrees. So what countries have committed to limit in terms of warming. So this would have obviously even much worse consequences than 2 degrees and higher risk of reaching tipping points, and would be actually beyond the range ever experienced by humankind. So the range ever experienced by humankind is 2 degrees. So major and immediate action can in principle still limit global warming and global heating of the Earth, and that's also associated change in climate extremes. In the end, this is our choice to make, and we have to remember that. And lack of action has direct consequences. Every additional year counts. So in the long-term solution, the only thing that we can do to stop this is to reach a net zero CO2 budget, which means no consumption of fossil fuels, no petrol, no coal, no gas. And I finish with this summary from IPCC that every action matters, every bit of warming matters, every year matters, and every choice matters. Thank you.
Thank you very much, Sonia. I guess there are questions. So let's try the first two rules here. Any of you are wondering something? It's a good chance to ask questions now. Who is brave enough? Okay, you think about it. So, yes, Eric.
Thanks, Sonia. It was a very nice presentation and a good overview of the subject. And I was just wondering about one detail. You showed in Europe, you talked about maximum temperatures, and you showed a large uncertainty range, and then you said that you didn't have time to talk about it. I'm wondering there, is that uncertainty mainly due to the fact that we are in between the areas of increasing precipitation in the north and decreasing in the south, or is it more to do with the climate models and how they represent the processes? And this is what my question really. Do you think that the models we are using are up to really giving us these detailed results in small areas like Central Europe, for instance?
Yeah, thank you. Yeah, that's a good question. I think part of the issue is that we have a clear signal of drying in the Mediterranean and wetting in the Northern Europe, so that's part of the issue. What we found was we have done an analysis with one of my PhD students, Martha Vogel, and we found that the models that are showing, so we found a tri-model distribution of climate models. We have some wet models that are not really drying a lot, not warming a lot. We have dry models that are drying a bit and warming a bit, and then we have very, very dry models which are reaching very high temperatures. What we found was the very dry models don't seem to be so realistic because for present climate, they're already a bit too dry. But also on the other hand, some of the very wet models are not so realistic. So we think we can reduce some of the range. So I would not say that it's in principle impossible to provide projection for this type of regions, but probably you need to also integrate some evidence from observation.